In this video, we're going to calculate the current associated with different operating regions of the MOSFET. This derivation is a bit gratuitous because we're not going to be doing a lot of device physics work in this class, but I think it's a really cool derivation. It goes from some very simple principles to some complex expressions, and it helps gets at the really fundamentals of what makes a MOSFET work. So the big trick to analyzing MOSFET current is to break the current down into a charge density multiplied by a velocity. Doing that requires some sense of distance to measure velocity, so I've introduced a distance dimension y on the drawing on the left. The y dimension refers to distance along the channel. The source is at y is equal to 0, and the drain is at y is equal to L. So a tiny little sliver of the channel would have a width of dy, and the voltage in that tiny little sliver we'll write as V of y. We start using our current times velocity formulation in the first line on the right of this slide. Drain current is defined as the change in charge with respect to time, which seems fine, and then we break that into the change in charge with respect to distance along the channel, multiplied by the speed of charge is going, how fast it changes with time. The Q of y in our dq dt expression can refer to charge anywhere in the channel, because we have to have current continuity at every point in the channel. Okay, finding the differential charge in the channel isn't so bad, because the channel is just a funny looking capacitor plate. And so we can find the charge on that plate using the capacitance density, Cox, so that's capacitance per unit area, multiplied by the x and y dimensions of our differential, which are W and dy. And remember that W describes the amount of transistor that runs backwards into the page. The dy in this dq expression is kind of convenient, because we have dq dy up here, so it'll just cancel out that dy below it. Next, we need to find the speed at which charge is moving, dy dt. Fortunately, we have a model for the velocity of ballistic conduction, which is conduction where carriers are running down a medium and bouncing off of stuff. And that's that the carrier speed is given by the mobility times the electric field applied to the carrier. Now, we don't actually apply electric fields directly to this, we apply voltages. We'd like to write this in terms of voltages at the end of the day. So we replace this electric field between the drain and the source with dV dy. Then we can substitute all of this together into a decent looking expression. However, this depends on channel voltages and a differential in y, and we'd like to get rid of those, such that we wind up with an expression in terms of terminal variables. So we'll take some integrals to get rid of them in the next few slides. I've copied the equation from the last slide here, and as I promised, we're going to take an integral to clean it up. I've moved the dy differential over to the left side, and because we're integrating against dy, we can integrate across the whole channel from 0 to L. That leaves us with a dV on the right side, so we have to integrate from the voltage at the left side of the channel 0 to the voltage at the right side of the channel VDS. Evaluating this, we get our first expression for drain current, and we find that it's parabolic. Great, we have parabolic voltage curves, current voltage curves. That seems sort of fine, but it's a bit weird that our current decreases at high VDS values. However, we did this integral in the linear and triode region, so maybe this decrease is kind of fake behavior, and adding in an analysis of a saturation region will explain what's going on. So let's see how the equation changes when we're in saturation. I copied our prototype equation from 2 slides ago, and we're going to do a different integral that captures saturation behavior. That integral is going to have different bounds because the voltage at the end of the pinch-off region here has a fixed value. Technically the length also has a different value too, because the pinch-off consumes a little bit of the channel. But we're going to ignore that here and talk about it more in the next video. So we rearrange our equation in the same way, but the bounds of our integral are different. We still go from 0 to L on the left side, noting that we're temporarily ignoring the small length defect caused by the pinch-off. But on the right, we integrate from 0 to VGS minus VT, because this is the voltage at which the channel falls out of inversion. Once the channel reaches VGS minus VT, there's no longer VT across it. Evaluating that integral, we get this expression for ID, which is also a quadratic. But this quadratic is not in VDS, it's in VGS. In fact, this expression is totally independent of VDS, which means that this will behave like an ideal current source. Now, one of the reasons I brought up this length approximation we were making is because VDS sneaks back into our equation through changes in the effective channel length, which is called channel length modulation. But for now, we don't see VDS anywhere. It's also interesting that this expression depends quadratically on VGS minus VT, which is called the overdrive voltage, by the way, this quantity. One factor of the overdrive comes from charge accumulation on the capacitor. So all of the voltage above VT results in additional charge piling up in the channel. The other factor comes from the fixed velocity of the channel being pinned by VGS minus VT being at the far end. And so if we now add in this saturation behavior to our ID VDS curves, that means we'll climb up like a parabola and then flatten out into flat lines as we reach saturation. I've put everything together on this slide. Equations for IDS in all 3 regions of operation appear at the top of the slide, and those regions of operations are illustrated on the ID VDS curves on the bottom of the slide. So this flat region with respect to VDS is saturation, the changing region is linear or triode, and then this line down at the bottom is cutoff. The equivalent circuit model is pretty simple. It's just a dependent current source between the drain and the source that's controlled by the voltage between the gate and the source. So this is our large signal model. I do want to add one quick reminder that we did this analysis assuming that the source and the body were shorted. If the body voltage isn't the same as the source voltage, then the threshold voltage changes slightly because charge in the channel sees a different total potential. And that slight change is called the body effect. So in summary, the MOSFET current is set by charge in the channel times the velocity of that charge. We set that equation up and then we take an integral to get rid of electric field, but the bounds for that integral depend on the voltages on the channel, which gives rise to 3 total regions of operation. And the expressions for those regions of operation appear here, as do their location on a ID VDS curve.